in this video we're gonna go discussing about improved DDPM, and we're gonna go focusing on this paper, and we're gonna go analysis on what's this paper brings in the field of diffusion models. So this is a I think this is second paper, second predominant paper. So it's not there are also many papers, but this paper actually has the additional top up on DDPM paper. So this paper is written by this guys, and we're gonna go discussing the brief summary of what this what this paper actually bring to us. So before going into the paper and every detail, I want to just give you a gist of what this paper actually bring, and what is the main idea of the paper, and what just try to get some of the main points that is bring, and then going into detail each topic is wise in the paper. So for that, first of all, we're gonna go do thorough in here. So each topic, what is bring and what's its help in short description, and then we're gonna go move forward. So they have shown that. So we in the original DDPM paper. So in this paper, so if I show you here, so original DDPM paper. So DDPM paper. And the paper, they so this is built on top of this paper. So on this top of paper, so this is the first paper in the denoising diffusion models. And after that, this paper in denoising diffusion model, then other we see that build on top of that. How can we improve? So they give some ideas here, some abstract ideas they given here, and here we're gonna go look at how can you improve the how can you improve the shortcomings of this model DTPM model which has published in 2020, and we're gonna go see how can we improve that models, and let's look at the summary part of it. So with we show that with a few simple modification, DDPM can achieve competitive likelihood while maintaining the high sample quality. So they are talking about likelihoods. So they are so diffusion models at that time in 2022, they generate samples which have high quality, but the log likelihood of the DDPM was not the competitive with the state of the art likelihood of all likelihood based on more other models. So while maintaining the high sample quality. So they have shown that with some modification we can achieve the competitive likelihood while maintaining the high sample quality. Additionally, we found that learning variances of the reverse diffusion process allow sampling with an order of magnitude fewer forward pass with a negligible difference in sample quality. So they introduced the when they are doing reverse diffusion processes, they are also learning variances, and it has allowed the sampling reverse sampling much more fewer than the forward processes. So with a negligible difference in sample quality, which is important for the practical deployment of these models. So if we in the forward pass and forward diffusion processes, we take 1,000 times step, and when backward we take 1,000 times step. So when we are sampling Gaussian noise of unit variance and zero mean, we sample some xt, and from that xt, from that xt, I'll show you. So from that xt we are trying to get this image. So this is our xt, trying to get this image. So we have to do 100 times iteratively remove the noise and get this image which fall in distribution QFX, which is our real distribution of the images which on which our data lives. And we additionally use precision and recall to compare how well DDPMs and GANs cover the target distribution. So for the whole coverage of the distributions, they uses the metrics like precision and recall to measure the cover of the distribution by both of them. And finally, we show that sample quality and high likelihood of this model or scale smoothly with model capacity and training compute, making them accessible, making them easily scalable. As the as we train more reasoning, as we train more and if we increase the model capacity, to capacity means we make the neural network even highly scaled and increase the training compute, we can achieve sample quality very higher, and we can get the likelihood and high likelihood also. And this likelihood is actually the measure. It is a good proxy of the mode coverage. So how the model actually covers have the how the model has covered the whole distributions of the data in high dimensional space. So and the first they introduce that they are using this learning the variance. So in our previous videos, we does not have the objective here. So if I show you the objective training objective, with which objective we are trained here, so in that we train with this objective. So there is no, this is just a, we are just predicting this mu theta, and so we are not predicting the, so this is the, if you, this is a function of epsilon theta. So you can, mu is a function of epsilon theta, and we are actually predicting mean. And and after that it is just a function of, so we can predict this epsilon theta to predict mu. So this is the approach. So we are just predicting the mean but not the variances. And and they say that to more tightly optimize the variation or lower bound, we learn the process variances using a simple reparameterization and a hybrid learning objective that combine the PLV with the simplified objective from Jonathan Hu and his collaborator paper. So they are just saying that to to optimize the variation lower bound to its optimality, they learn the reverse process variances using a reparameterizations, and they introduce, this is as simple means this objective. This is the simple objective. This is the as simple objective which does not depend on the variances. So not this, I will show. So this is the objective. So if I can show you. So this is the as simple objective. So this is the objective I want to show you. So this is their objective. This is the as simple objective they're talking about. So they, this is the L simple objective, and this is simple objectives, which does not care of the variances. The variance is set as hyperparameter, and so in this we gonna go LB. LB is a term. So if I can show you, so if you have watched the previous video, you can understand what LV is. But I'm gonna show you. So this is when they're doing optimizing training. So your LV is in this paper. There is something. So this is the term. So this is the LV term. The whole, this is the LV. So and this is LV. So this will contain this terms L0, L0, L1. So here, so this contain this L0, L0, L1, and other terms also here involving here. And so this is the, so they use this LV, which will help us to learn the variances also. So this LV, from this LV, we're gonna go learn the variances, and this parameter we're gonna go learn. So, and this is our as simple as I've showed you here. So they are gonna be using this objective, so which combine this LV term, and which will gonna go help us to determining the variances. And the simple we have, and this is lambda. This is some hyperparameter, and this is for weighting. So for weighting, which terms to weight high and which term to weight low. So this is the overall. This is the high. This they call this as a hybrid objective in the paper. So, and mm, if you can so if you mm, yeah, so if you optimize this variational lower bound, so this is our variational lower bound. So in the variance form, in the variance reduction form by rewriting. So this is the objective. So they're just dividing in each section. So this has this is the whole term which consists this L0 this, and LT minus 1 is this, and LT is this. So they're just giving it like in this way. So and and we're just considering in the previous video, we're just considering this term. This is the reverse reverse of the forward diffusion processes. So, and this is the our approximate reverse diffusion processes, and this is actual. So we want to match the movements so of this both. So we're gonna go. So we want to make these two conditional distribution as close as possible, and and if we able to match this KL divergence, we can actually get our model which can generate the which can actually undo the reverse undo the forward processes and get the samples from get a sample. And so let's move into the second part, which is the improving the noise schedule. So in the original DDPM paper they propose a linear noise schedule which add noise linearly in a linear fashion. And when you do that, this is the effect of linear schedules. You can just see here we start with the dog, and as we know, we in the diffusion model we add noise and destroy the structure of data and try to recover the structure of the data back and get something which lie in this the distribution of the dog. And if we start with this image and try to destroy the so we have to destroy as slowly as possible, because why when we are just when we're trying to reverse this, so if we are just add noise from here to we are just going to here, so this is very hard for the model to learn or mimic this transition. So we if you goes in the if you have in the most more for steps, since we can learn easily and get our model capable of removing noise. So we want to we doesn't want to destroy the structure as quickly as possible. So first of all, we start with the image and add noise in this linear fashion. So if you start with this, if you go with this is the what happened when you start with this. So from here, I think you are just here from here the structure of it are from here to here. I think year to year, this is completely destroyed from year to year. So this destruction is very quickly, and if you try to reverse this destruction, this this reconstruction, so reconstruction, this is very hard for us to do that reconstruction. because this destruction is very huge, isn't it? From year to year. So this is, so for model to predict this from year, so this is pretty hard. And from, so we want to just, we want to make this transition between two steps easily, so easy, so that our model can remove this. And this noise removal is actually helping us to go in the directions where our data lies. So if we are doing, so we are just removing the part which does not lie on our, so we does not lie on our distribution set. So distribution, so this is the, and if we start with this linear, this is linear, and this is cosine. So if we start with this cosine schedule, and the author has proposed the structure of the data, you can see here we are not actually destroying it. So I think for here we are just going something here, like something like here. So we are actually not destroying the data at such a rapid pace. So from here, and you can just hear there is so much resemblance, so you can just stop here. So also, because from, if you go from here to here, there is, I think there is no any structure present from here to here. So, and if you gradually destroy the structure, and this is a better while reversing the diffusion process. So here the reverse diffusion is very easy, because the model has to predict little bit of transition here. So not that actual transition from here to here, you see, from here to here, you see there is big transition. And here this is just simple. So this is nothing, this is just a very trivial thing here. Just we are, we can just stop it here also. And and this is a graph of this alpha bar t. So this in, so what this alpha bar t is actually dictate how much original data remains after t steps, and how much noise is added. So this, if you look at here, so this will tell, so you take the this x0, and how, and how, so this will just gonna go add by something 0 point, so in its your pixel, so it will just gonna go multiply with 0.001, and each pixel will multiply by this value. So this value is, we're gonna go scale down your mean, and and how much original remains after each steps, and how much noise is added. So, and in the reverse process, so, and this is gonna go, this is our variance part. So if you, if you go to the, this t value become much more higher. So if this t become like 100, this is final step, so this will approximate to 0, and this, the variance of the distribution will approximate to 1. So which is a normal distribution, so which you want. And in the reverse process, this alpha bar t helps the model in removing the noise step by step to recover the original data, controlling the mean and the variances of the reverse steps. And you can just see here also, so this value is, it's not like it's something like exponential, not exponential, but this is sort of like exponential. So you can just see it. So, and this is the linear, this is a cosine. So this cosine is actually helping us. So it is not destroying the stocks of data quickly from year to year. It's not destroying the data quickly. You are here, and you are just destroying directly here. It's such a quick transition between this from year to year. So this is transition. So here you can see the linear transition, so slowly transition from each step. So this is such a slow transition here. And and and, and this is so we are diffusion. So we are diffusion steps. So alpha t, this graph will, this graph will tell us all this above is telling us cosine, and this is telling us the linear part. And they're gonna be using something called importance sampling. So So impedance sampling. So what they use the gradient noise. So if I have already tell you the hybrid objective. So while training with this objective, this LB objective, they encounter much more gradient noise, so which is not good for the model. So gradient noise means the noise are not clear. So the gradients updation are not clear, and they are using this important sampling technique. They improve the gradient noises and gradient noise of LV loss. So, and they yeah, and to understand this, what they have done. So if you have the understanding of importance sampling in statistics, it's nice. So this is actually the so improved DDPM ever introduce a noise schedule that gives more weight or priority to these important noise levels. This is this is same as to adjusting the proposals distribution in the importance sampling. So in importance sampling we propose we adjust the proposal distributions as this is same as this. So and by focusing on a critical noise level, the model can learn more. So we are going to focusing on the more critical noise levels, the model can learn more efficiently, reducing the overall error in the denoising process. So this is, I think, we are just and if I so yeah. So this biasing mechanism, so this focusing on the critical noise level and model can learn more efficiently and reducing the overall error in design. So this biasing mechanism act like an important sampling procedure. By sampling more frequently from a critical noise level, the model efficiently reduce the variance variance in its gradient estimates, leading to better convergence during training. And they have also given some description here. So we are going to focusing on the particular level of this of the reducing processes. So and so we going to bias to our some of the processes, and we going to help that in that part. And noise schedule is adjusted during training to favor certain noise levels over other. This is achieved by modifying the distribution from which noise is sampled. So this can be achieved by modifying the distribution from which we sample noise, essentially biasing its towards noise level that are more significant for the reverse process. So and if we are in some steps like I will give just 50s, so you are just from 50s from transitioning in that, so you are getting hard time for transitioning in that step in 50 steps. So you're gonna focus your resources on much more on that using this important sampling techniques. And and other improvement, this paper also introduce some of the other improvements. And so first of all, they want to so that so and they want to first of all so that they want to achieve high likelihood as other likelihood based model, and their main goal was to is improving the log likelihood of the data. And this measure is very good proxy of the mode coverage. And how this cover the how this cover the overall distribution of overall data distributions. And this log likelihood matrix, they try to improve it. And there is this is the main goal of this paper. And the other improvement for the applicability, so they improve sampling time. And with the variance, so they have learned the variances, and variance help to improve the and scalable model size. So we explore how performance scale if we reduce the steps during sampling. So they reduce the steps during sampling and find that our pretend hybrid model can produce high quality sample with many fewer diffusion step than they were um, trained with means forward processes. So without any fine tuning, reducing the steps in this way make it possible to sample from our model in a number of seconds rather than a minute. So I greatly improve the performance of the practical ability of the image DDPM. And another they have given is so they also try this implement this trend also, so, scaling model size. So as we make our model larger and deeper, and if you devote much more training time, it has empirically seen the model improve the performances, and this is also same as predictable as in the as the other model also. So they say that DDPM improve in a predictable way as training compute increases. So this is the, and they have also given some other thing also, comparison to GAN. So we're gonna look at the comparison to GANs also, and here's a summary of this. So we have shown that with few modification, DDPM can sample much faster and achieve better log likelihood with little impact on sample quality. So the likelihood is improved by learning this variances using our parameterization and L hybrid objective. So they say that the likelihood is improved by this, and this L hybrid objective. So you using, so they're gonna go learn this. They're gonna go learning covariance this covariance theta. So and this will gonna go so this can be learned using parameterization and their proposed L hybrid objective. This brings the likelihood of this model much closer to the other likelihood based model. We surprisingly discover that exchanges also allows sampling from this model with many fewer steps. So they say that with this learnable variances, they can sample much faster. Uh, and this is the overview of the paper. So let's deep dive into the paper. So we're gonna look at this paper, and this is written by the guys from OpenAI. So these two guys, and they are doing phenomenally well in this domain, and they are publishing many resource paper as well. So let's look at some of the abstracts. So let's look at the abstract part of it. So are the class of generative models which recently been shown to produce excellent sample. We have already know that, and we saw that with few simple modification they can achieve competitive log likelihood while maintaining high sample quality. And they additionally find that we can find that learning variances of the reverse diffusion process allows sampling with an order of magnitude fewer forward passes with negligible difference in sample quality. So learning variances help to sample fastly, and which is helping the practical deployment of these models. And we're gonna so they are using precision and recall to compare the how they cover the target distributions, and we show that sample quality and likelihood of this model scale smoothly with model capacity, training compute, and easily and making them easily scalable. They are highly scalable as we look at in the first video. So and they are scalable, and they if we increase the compute, they they will be they, they give predictable results. And they are just giving some introduction. Mm. So I think this is a good thing to again get the understanding of it. So it's a class of generative models which matches the data by learning the reverse gradual multi-step noising processes, and more recently shows an equivalence between the denoising probabilistic model and score based generative model. So this paper so we're gonna focus on this paper also, which is score based generative models, and we which learn a gradient of the log density of the data distribution using denoising score matching. This it has recently been shown that this class of model can produce high quality images. So we're gonna go in the next video. We're gonna look at this score matching also in upcoming video, and they're gonna using this CFAR10 and this Lucian dataset for it, and in this paper in the previous paper we tested with the CFAR10 and Lucian dataset, and but this is they have already this model DDPM was trained on, so the extremely good result in CFAR10 and this bedroom dataset, It is unclear how well DDPM is scaled to the higher diversity such as ImageNet, which has thousands of classes, isn't it? Which has thousand classes. And finally, while found that DDPM can generate audio using a small number of sampling steps, it has yet to be shown that it is same true for images. So how can we generate? So if we haven't tested at that time to the diverse dataset, and in this paper we show that DDPM can achieve log likelihood with competitive even on the high diversity dataset like ImageNet. So in this paper, these guys show that this model can get competitive log likelihood like the other likelihood based model, and they can perform well in the high diverse which contain multiple classes of images like ImageNet. And to more tightly optimize the variation lower bound, we learn the reverse process variance using a simple reparameterization and habit training object that combine the VLB with the VLB loss with a simplified objective from this guy. So they're gonna add they're gonna create this hybrid learning objective using this VLB with the simplified form of simplified loss objectives. So, and if when we are optimizing this L hybrid, so uh, we are we are focusing also on likelihood. So when we are just doing this simplified objective, just predict noise, it does not helps in variance. There is not directly help in the likelihood. When you learn with this hybrid objective, we are also focusing on the log likelihood of the models. So we find that our hybrid objectives, surprisingly, we found that with our hybrid objective, our model can obtain better log likelihood than those obtained by optimizing the log likelihood directly. And so their hybrid objective, what I have shown you earlier. So if I can show you earlier, so this is a hybrid objective. This is a hybrid objective. So, and I've also shown this what is this LV term, and this lambda will gonna go. This is a waging term. So, and what else they are saying that, so with their hybrid objective, their models, our model obtain better log likelihood than those obtained by optimizing log likelihood directly, and discover the latter objective much more great night during training. And this latter objective, this another VLV objective has much more gradient noise during training, and we show that important sampling technique, simple important sampling techniques reduces the noise and allow us to achieve better log likelihood with the hybrid objective. So they are saying that in in the latter objective means the VLV objective, they see that much more gradient noise, and which is not good for the training, and they use something called important sampling to reduce it. And after incorporating log variance into our model, we surprisingly discovered that we could sample in a few steps from our model with very little change in the sample quality. And they saying the 100 of this DDPM, original DDPM requires 100 of horror passes to produce good sample, and we achieve the good sample as few as 50 horror passes. So they are just reducing this the boss processes by high order of magnitudes from hundreds, nearly thousand, to they are just coming into the 50 forward passes, and thus speeding up sampling for in practical application. In parallel to our work, develop and different approaches to fast sampling as we compare against their approach. So, and this DDIM paper is developed by these guys, this song and his collaborators. So in the parallel work to their work, so they develop something called DDIMs in models. So this is a different approach to fast sampling. So this is, and they are just, they can produce high quality sample just in less time also. And so they compare with their, so they also compare with this DDIM approach in their experiments. And log likely is a good metric to compare against other likelihood based model. We also want to compare the distribution coverage of the model with GANs we uses. So So likelihood is a good matrix. So they also want to cover this distribution coverage of this model, and with the use of this improved precision and recall matrix. So we use this improved precision and recall matrix and discover that diffusion model achieve much higher FI, much higher recall for similar FID. So this recall will actually tell us the mm, yeah. So they discover that diffusion model achieve much higher recall for the similar FID. So recall is actually responsible for the how how it's how it's cover the overall entire distribution. So for similar FIDs. So this is the also another matrix for MS, and this is actually tell us that this is also matrix for diversity. So uh, how diverse it's cover the distribution. So this factor will consider the diversity and suggesting that they suggesting that they do indeed cover as much larger portion of the target distribution. So and by using this metric, they suggested that they cover much more of the target distribution. And finally, since we accept machine learning model to consume more computational resources in future, we evaluate the performance of this model as we increase the model size and training compute. Similar to, we observe the trend that suggests the predictable improvement in the as we increase the. So they are telling that we increase the compute and our model performance also go up personally. So this is the denoising diffusion probabilistic model. They are just giving description. So so they are given some data distribution, this q of x0, and we're gonna sample this. We're gonna take this x0 and we're gonna define this forward noising process. This forward process is defined by q, and this will gonna produce the latent from x1 to xt by adding Gaussian noise at time t with variance between this as follows. And this is the forward processes. So from x0 they're gonna go create this latent variables, and this is represented by this joint is represented by this multiplication sign. This is one of the thing from 1 to t. We're gonna multiply this, and this quantity here is actually can be computed in a closed form. So which has this closed form, if you integrate this quantity, so we can just compute this quantity as well. So this has this form, this closed form. And they are saying that if just I'm also giving some of the brief overview to again, and if you just repeat the concept as you read from different people, your understanding will become much more better. So I'm again repeating it. So we are already covered the forward and backward processes, but I think this technique is very efficient and used in other domain also, isn't it? And such as marketing. And so if you increase this large T and have a OLBF schedule of beta T and let an XT, and is nearly an isotropic Gaussian distribution. So if you just increase the t and a good and you have set this beta parameter perfectly, isn't it? You can just get obtain this xt, isn't it? If you have last t and set this at a proper way, you can get this last step as nearly isotropic Gaussian. So means it has all directions, same intensity at all directions. So isotropic means have the same property across the whole distribution. So and which are the mean, zero, and unit variance. And thus if we know the exact reverse, this is the forward process, and if we know this exact reverse distributions, we can sample xt and run the processes in the reverse to get a sample q0. So since this depends on the entire data distribution, entire this depends not only the our sample, but it depends on the entire the data distribution. I think this is does not we can't approximate it, so we can't get this values in. So we need the entire data distribution, so our training sample will not gonna help us here. See, there's few samples, so and with our few sample we can approximate, we can do that essence. So we doesn't have this whole images of the distribution, but we can make the neural network to approximate this. I think this is the real power of the neural network. So we can approximate using this neural network mu theta and this sigma theta, which will help us to find out the mean and the variances of this transition. So and the combination of p and q and p is a variational autoencoders, and we can write the variation lower bound as follows. So this is the derivation is same since. So the Q is a reverse process. So and the P is a forward process. P is a Q is a forward process, and P is the reverse process. And they can, as we do in a variational autoencoders, we're gonna go using this variational lower bound here as well, and this will gonna go tell. So if you just do, if you start from the log likelihood of the model, so if you start from here and optimize it and make a bound, and you're gonna go obtain this. If you do some calculation, you're gonna go reach here, and this has the form, which is called variance reduction form. So and if you optimize this, starting from here, we're gonna get this term. So we're gonna getting this term. So VLV is the overall all this term here. So all this term, this is VLV, and VLV contain this, and L0 is, we know it, so as here, and LT minus 1 is this, and LT is this. So guys, let's move into this part, improving the log likelihood of the model. So in this section they will gonna go focus on how can you improve the log likelihood of the model using some algorithmic changes. So this is the main idea of the paper, and this is the main goal of this section 3. So from 3.1 I think they will show some, so you can hear. So if I there you can share. So in this section, in section 3, they were gonna go introduce this learning, this 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 thing here, this thing here, and after that they were gonna focus on learning this variance of the reverse diffusion process, and after that they're gonna go improving the noise schedule. So and they were gonna go focusing on how can they were gonna go focus on reducing the gradient noise. So and after that uh, and they will gonna go move at the result and evaluation section, and this is the main goal of this section 3. So let's focus on first part. So learning this value. So this sigma theta, they will gonna go learn this value sigma theta. So let's gonna focus on that. So in the original paper in 2022 paper, the author said this quantity as this, where this quantity is not ln, this variance, this is and this is actually, if you square it, so this will become variance, and it's not ln. Oddly they found that fixing this quantity is equal to this yielded roughly the same quality as fixing this as a posterior. So this is the forward beta t's, and if you use if you feed this as this quantity beta t, they will gonna go yield the result, same result as this beta tilde, which is the posterior beta tilde. So and by learning this, by fixing this, uh, they get reasonable samples, and they are given some graphs here. So beta tilde and beta tilde the posterior quantity, and beta tilde is the forward quantity. So if I erase it, so this is a graph, and this is on the diffusion step, and this ratio they have given. After that we're gonna look at the let's focus on another part. So and they are given this curve as well. So Bayalvi versus diffusion steps. So let's move on to that fact. So considering this quantity, this and this represent two extremes, it is reasonable to ask why this twice does not affect the sample. So this quantity is actually the forward and this quantity is actually the posterior one, posterior beta t. So and fixing this which represent are two extremes, so they are actually opposite of each other, and it's reasonable to ask why it does not affect the sample quality, and they give the clue in figure 1. So in figure 1, the beta t and beta tilde almost equal near t is equal to 0, so they are saying that are almost equal except this t is equal to 0. So at all the diffusion steps, the this values of beta tilde and beta tilde are same, so it does not matter by setting this quantity as beta tilde. So we can just fix it as this, and we doesn't have to approximate this beta tilde through our neural network. So they are saying that, so we can fix this quantity. So I can just write it beta tilde. So where the model is dealing an imperceptible detail. So at t, that where the model is, so imperceptible detail. Furthermore, as we increase the number of diffusion step, beta tilde and beta tilde seems to remain close to one another from for more of the diffusion process. This suggests that in a limit of infinite diffusion step, the choice might may not alter for the sample quality. In other words, we add more diffusion steps. The model will focus on this quantity while determining the distribution much more than this quantity. So, if you consider this, if you consider the very large diffusion steps, so we can just skip this term. We can't if you does not learn this quantity and learn this, this is gonna determine the distribution much more. This is the learning, and they are saying that fixing this is reasonable for the sample quality, but it does not say anything about likelihood. So we want to make our likelihood better, but fixing this does not give any clue about the likelihood. And so if you learn this, in fact, figure 2 shows that first few steps of the diffusion process contribute the most to the variational lower bound. Thus, it seems likely that we could improve the log likelihood by using a better choice of this quantity. To achieve this, we must learn this. So they are saying that if you want to improve the log likelihood of the model, you should learn this quantity, and without any instability encountered by these guys. So since figure 1 shows that the range of this is very small, so it will be hard for the neural to predict this quantity directly. So even in a log domains, as they have observed by this guys, so we can just move on from here. So this is the learning part of this variance part. So we can, if you learn this, we're going to improve our log likelihood of the model. And let's go on to the another part, which is, and they are also defining something called, so in particular, our model output a vector v. So vector v containing one or more component per dimension. We turn this into a turn into a variance as follows. So this quantity is evaluated by this. So the model will output this quantity v, vector v, uh, and we're gonna compute using this formula. So this quantity is computed by this formula, and v is actually calculated by the model. So 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 uh, we found it better to parameterize. Instead, we found to parameterize variance as an interpolation of beta t and beta tilde in the log domain. So they are telling that uh, rather than just uh, so they are saying like we can better better parameterize the variance as an interpolation of, if we parameterize the variance with the help of combination of this both quantity, we can actually get better variances rather than just using the beta tilde. So in the log domains, and the model will predict this vector v containing one component per dimension, and we turn this out output into a variance as follows. So they are just telling that if we don't apply any constant on v, theoretically allowing the model to predict variance outside of the interpolated range. So we don't need that. And for the so in the Jonathan Ho paper, the first paper of DDPM 2020, so DDPM paper, so these guys are just using L simple loss, which is the mean square difference between the actual and the predicted. So actual and the predicted. So in this Jonathan Ho and the other guy paper, they suggested that this objective. So they're gonna suggest that objective they will gonna go from expect x0 t and something this epsilon t. So they are just and squaring it. So they are just as simple as objective is this. So this is the just a mean square error between the actual noise and the predicted noise. This is as simple. So and LB is the LB is the total objective. So L0, LT minus 1 as I've shown you earlier. And they have said lambda as this, which is actually a weighing term. So this will just control how much the control this have over this. So this if we set the lambda higher, then it will dominate this quantity as simple, and it will be tuned according to our requirements. So and they are also saying that so they will to prevent this LVLV from overwhelming L sample. So s- along this same line of reasoning, we also apply the stop gradient to the output for the LVLV term. So they are also stopping the gradients of this of this object to actually overwhelm this quantity LVLV. So we are not overwhelming this, and from this we are not also overwhelming this quantity, this LVLV term. So and this way LVLV can guide this quantity. So this LVLV loss will gonna guide us to learn this quantity, while L symbol is still the main source of influence over this quantity. So it will not gonna go affect the LVLV will not gonna affect mu theta of xt comma t, it and the main source of this will be L simple loss. And so let's focus on the second section, which is improving the noise schedule. So we found that while the linear schedule used by this guys Jonathan Ho and his collaborator work well for the high resolution image, it was suboptimal for the image resolution. It's not performing as well as the for the this resolution, and in particular the end of the forward noising process is so, too noisy. So it does not contribute every very much to the sample quality. So I will gonna as I've already shown that. So it does not contribute very much to the sample quality. This can be visually seen in figure 3. So let's look at the figure 3 before visualization. So in figure 3, figure 2, figure 3. Sure is our figure 3 is here. So they are saying that, so we have already discussed that. So the end of the so as you go to the end of the forward noising process, it's too noisy as you can see, and it does not contribute to the learning of the model. So and it does not contribute very much to the sample quality. This can be visually we have already seen here. The result of this effect is study in figure 4. Figure 4. So you can hear FID. So how and this fraction of reverse diffusion process is skipped. Fraction reverse diffusion process is skipped, and where we see that a model trained with a linear schedule does not get worse, does not get much worse as measured by FIT when we skip up to 20% of the reverse diffusion processes. So, and to address this problem, we construct a different noise schedule in terms of alpha bar t, and so they're gonna propose this schedule which is dependent on which is a which we're gonna use the cosine function to, and this will gonna take this quantity here, and it's gonna give this value of alpha t for the particular time step t. So to go from this definition to variance beta t, we note that beta t is this, this is the previous, and this is one step later, and this is one step ahead of this quantity above. And in practice we clipped to be no larger than this to prevent singularity at the end of the diffusion process near t is equal to t. So we can just go further and mm, 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 mm. So main idea is that they use this cosine which gives the steady value of the cosine, this is alpha bar t, alpha alpha t bar. So this alpha this quantity is decreasing gradually and gradually. So our diffusion process will be also here. So you can here observe here. So this will also get worse, or this will also get noisy in a steady way rather than this slightly this exponential, little bit of exponential, not exponential, but you can just see here. This is a very unstable while adding noise. And let's move into the reducing the gradient noise. So they expect to achieve the best log likelihood by optimizing this LVLV directly rather than optimizing this L hybrid. So LVLV is the original loss, and L hybrid is a combination of LVLV plus L simple. So L simple, and this is weighted by lambda, and this is gonna be the L hybrid, and this is LVLV, and this is the L hybrid is the combination of, this is addition sign, guys. This is addition sign. So and this is so they have the intuition about that is, while if they optimize this quantity LVLV, they will gonna achieve this best log likelihood. And because this section will focus on how can they improve the log likelihood. So this in this section they find that this quantity is very difficult to optimize in practice. In the diverse data set like ImageNet 6464, it's a resolution, and this is giving the size of the images. So and the learning curve for the both L hybrid both are noisy, but the L hybrid objectives achieve better log light on the training. That's it. Also, they're saying that this the LVLV and L hybrid curve curve actually, the gradient signal coming from there is very noisy, but for this LVLV the gradient signal is much more noisy. So they are also hypothesized the LVLV, the gradient signal from much noisier than that from L hybrid. So the gradient noise is noisy, so this is not good for the model. So but from this LVLV, they're getting much more noisier, and when they optimize this quantity, this LVLV loss, to obtain the best likelihood, but they see that the LVLV loss actually giving much more noisier gradients, and it's hard for the model to make the process efficient and better. So and they confirm by evaluating the gradient noise scale as given here. So gradient noise scale they are given here. So gradient noise scale you can see here. The L hybrid has much more lesser gradient noise, and this quantity LVLV has the much more. You can see here this have the higher gradient noise this than this. So they validated by this gradient noise scale here. So and this is the training steps. And what they are given here, and thus we sought out to reduce the variance of the L value in order to optimize directly for the log likelihood. Noting that the different term of LVLV have a greatly different magnitude, we hypothesize that sampling T uniformly cause L value object. So they are saying that our sampling of T, our sampling of T, sampling T uniformly actually cause this high variance problem. So high variance problem or this gradient noise. So our we were sampling this T uniformly, which caused the unnecessary noise. So they're going to apply the something called importing sampling. So to understand it without any mathematical just intuition, you know, just in a mathematical intuitive way. So if you are doing some sort of this is so if you are doing the reverse process, you start from noise, something called noise, and this is pure noise. So you start from noise, and from noise you want to go back to the real looking image, guys. Real looking image. So from noise you want to go real image, and there is some steps. So in this step the model is struggling so to recover the actual predict model is actually finding hard time for actually how much noise it added at that time step, and it is unable to recover the actual noise added at that time step. So so we're gonna focus on this term. So we're gonna dynamically update. So we're gonna go dynamically model, and dynamically we're gonna go focus or give more priority to this diffusion steps. So this is the intuition about important sampling. And so with this technique they optimize, so they are given. So with this objective they are able to achieve best log likelihood by optimizing LVLV. So using this important sampling and using this LVLV loss, and they are getting best log likelihood. This has been shown in the figure 6 as LVLV erase sample. Figure also shows that important sampling is considerably less noisy than the original uniformly sampled objective. And they found that this important sampling technique was not helpful for the L hybrid. This is helpful for the L VLV. And so they are also given in some result and evaluation. So you can just I'm just skipping it. And let's look at another term. So and they're gonna focus on this improving the sampling speed. This is the main another main idea of that. So how can you improve the sampling speed and improve the practical applicability of the DDPM? So for that they are saying that they train the diffusion model with 4,000 diffusion steps, thus producing a single sample takes several minutes on the modern GPU. In this section, they guys explore how performance scale, so how performance changes if you reduce the steps during sampling, and find that our pretend hybrid model can produce high quality sample with fewer diffusion steps than they were actually trained with. And reducing the steps in this way makes it possible to sample from our model in a number of seconds rather than a minute, and greatly improve the practical applicability of the DDPM. And they're gonna go give this quantity here. So if the model was trained on this T diffusion steps, so and we should typically sample using the same sequence of T. And it is also possible to sample using arbitrary subsequence of as of T values. And given the noise schedule this alpha bar T, for a given sequence, as we can obtain the sampling noise schedule, this sampling noise schedule. So this is a new sampling noise schedule. This is so we are focusing on the new subsequence of T. So this will not gonna focus on this 1 2 3, and we're gonna focus on the next subsequent. And this is a subsequence as of T, which is this from rather than going from 1 to this, T. So we're gonna focus on this one we are sampling. So we can obtain sampling noise schedule this, which can be then used to obtain the corresponding sampling variances. This is sampling variances, so corresponding sampling variances, and we're gonna be using this step rather than going from this way. We're gonna focus on this way while sampling step. So we're gonna apply this sampling step rather than the full which we have trained the model. So and these guys are telling us now since this is parameterized as a range between this quantity, so this is the range upper and lower bound of this beta, this variance, so beta, and it will automatically be rescale for a shorter uh, diffusion process. So we are just giving the bound and this will automatically changes changes for the shorter diffusion step. So this values will be this alpha bar, alpha where is our, or this quantity will automatically adapt in this in their own ways because we have make the make the range between this, we can just define this range, so they will gonna automatically rescale for sort of diffusion process, and they will gonna calculate this quantity as this from this they will gonna sample this quantity xt x of st minus 1, and they will gonna sample from this Gaussian distribution which has mean this and the variance this. So and to reduce the number of sampling step from t to k, we use the k evenly spaced real number between t and k. So they are saying that if you want to reduce sampling step from t to k, they will gonna go evenly space real number evenly spaced by k between 1 and t, and they are saying that, they get mm, they evaluate, they will FIDs for the L hybrid model and L simple model uh, that were trained with 4000 diffusion steps. 4000 4000 diffusion steps. So using sampling steps, so they're gonna go use employ this sampling steps. We do this for both fully trained checkpoints and the checkpoint midway through training, and they found that where they are. So with this model 100 sampling steps is sufficient to achieve near optimal FID for the fully trained model. So they are saying that by using this mechanism here, rather than sampling from the whole, by just sampling from this sampling from this subsequence as of t, rather than using this they will gonna employ this 25 50 this, and they are getting near optimal FID with the lon sigma. So L hybrid in which we learn the sigma theta, we learn where we learn the sigma theta, the model is actually producing high quality sample, but in the L simple model where we does not learn the variances, the sigma theta, the model is not producing convincible out, and they're also just referring the DDIM is diffusion, denoising diffusion implicit model, and they will gonna use something called OD rather than SD, which is stochastic differential equation, and this is coordinate differential equation, and they're gonna go imply this, and this is actually a very efficient way to sampling, and this will actually within 50 steps we can get the reasonable sample from this DDIM. Yeah, within the 50 reverse sampling steps we can get the optimal good looking images, in which we get we spend nearly a hundred, nearly a or not 100 but 1000 time step in the DDPM model. So DDIM is just mm, some, so we're gonna focus on this quantity, and it has some different property also. We'll also gonna discuss this property in the later one. So these guys, this Yan Sung and this his collaborator proposed this fast sampling algorithm for DDIM by producing a new implicit model, this implicit model DDIM, and they are saying that they have the same marginal noise distributions, but deterministically map noise to image. So they will gonna go not stochastically, they will gonna go deterministically map any noise into the image, and we include their algorithm DDIM, finding that DDIM produce better sample with fewer than 50 sampling steps, but Ors sample when 50 or more steps. Interestingly, DDIM perform Ors at starting of the sampling, but if we train enough, then it will gonna go give the convincible to other samplers. And there, so this is a mm, mm, mm. And let's focus on the another part, which is comparison to GANs. So comparison to GANs, it is in that time nearly this paper was published in 2021. So in that time, it's the GAN is holding some of the records of the some SOTA results. So it has some of the state of the art results by in FID or any other inception score, some of the metrics in likelihood. So these GANs are actually holding the records in the image generation. So and they are doing comparison this with the GANs and they improve DDPM. So and they are saying that while likelihood is this likelihood is actually a good proxy for the mode coverage. It is difficult to compare to GANs with this matrix. So they are saying that likelihood, as I'm saying, likelihood is a good proxy of mode coverage. So mode coverage means how it's covered the entire distribution. So with this matrix, they are finding difficulties to measure to compare the comparison between GANs and diffusion models. So they turns into this precision and recall matrix. So since it is common to in GAN literature to train class conditional models, so they did the same, and they also gonna go use this conditional diffusion model. And for the class conditional, so they will gonna go inject the class information through the same pathways as T. In particular, we add a class embedding this to the time step PT, and we pass this embedding to the residual block. So they are saying that as the same way we inject the time step information, we're also going to inject this class information in the residual blocks into the residual blocks. So and this is they're gonna just training some conditional diffusion models by injecting classes and the time steps. So and the GANs. Mm, 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 mm. So So let's focus on another part. So throughout the model, so they will gonna go inject the time step and the class information throughout the this residual blocks. So let's guys move into let's we train we train using this L hybrid objective you with and use 250 sampling steps. We train two model, a small model with 100 million parameter and this many training steps, and model with this many parameter and this many training iterations, and they will gonna compare with the big GANs which have 100 million parameters across the generator and discriminant. They're gonna compare with this big GAN deep and outperform our smaller model in terms of FID, but struggle in terms of recall. This suggests that diffusion models are better at covering the mode of the distributions than comparable to GANs. So these are saying that big and deep outperform their smaller model, not bigger model. So in terms of FID, but FID means the diversity, but it's not actually the FID, but it will also focus on the other aspect. But in terms of recall means the actual coverage of the distribution. Uh, they perform and they struggle this big and deep struggle, and this suggests that diffusion models are this is actually the matrix real matrix for the mode coverage. So they are saying that covering the most of the distribution. So recall is actually the recall of the diffusion model is actually better than the GANs, which we see that diffusion models are very better than GAN in covering the entire distributions, most of the distributions. So and they are saying that scaling the and let's focus on the next section, which is scaling the model size. So in this section, so in the previous section, we saw some algorithmic changes that improve the log likelihood and FID without changing the amount of training compute. So in the previous section, as we are read, we do some algorithmic changes and improve log likelihood of the model and FID without any amount without with same amount of training. So without any changing the amount of training. So in this section, as the modern trends say that if you make your model larger and spend more time on training, you get better performances. So in the section, these guys will gonna scale the model and increase the training times to make the model more applicable in the real world. So these guys are telling that, however, a trend in a modern machine learning is that larger model and more training times tend to improve the model performances, as uh, as these guys are saying. From and given this observation, we investigate how FID and NLL scale as a function of training compute. Our result preliminary suggests that DDPM improve in a predictable way as the training compute increase. So if we increase the training compute, this will also going to improve in the predictor way, and they are saying that. So they're saying that improve relative to the theoretical training compute. FID curve look approximately linear on the log plot, suggesting that FID scale according to power law, but this NNL curve does not fit a power law, as clearly suggests that validation analysis skill is in a less favorable manner. So, and this NLL curve does not fit the power law, but FIDs fit the power law. So this is the and such as unexpected high irreducible loss for this type of diffusion model. Two is the model overfitting the training distribution. So why this happen? Why the why why this quantity, this NLL does not increase as expectedly according to the power law? So these are some of the reasons. So we're not going to focus on that. So let's do some of the conclusion part. We have already do, but again let's do the conclusion part here. So they are saying that if we make some modification in the DDPM, such as implementing cosine noise schedule, and learning this sigma theta, and reducing the noise, we can achieve better log likelihood, and we can and if our likelihood better, better log likelihood, and we can also sample at much faster steps with a little impact on sample quality. Likelihood is the improved by learning this quantity, and we're going to learn using some parameterization and a hybrid objective, and also going to and this brings, so we're gonna go, apply this L hybrid to learn this quantity, this this quantity. We're gonna use our requirements and use this L hybrid objective rather than L simple. This bring the likelihood of this model much closer to the other likelihood based model. We surprisingly discover that distance allows sampling from these models with fewer steps. So, and they're say telling that's other thing also. We have also found that DDPM can match the sample quality of a GANs while achieving much better mode coverage as measured by recall. Furthermore, we have investigated how DDPM is scaled with the amount of available training compute, and found that if you devote more training compute trivially leads to the better sample quality and log likelihood. So if we in a straightforward way, if you increase the training compute, you will get gonna go better sample quality, and your likelihood log likelihood gonna go increases. So this makes the DDPMs DDPM so this makes the DDPMs a promising direction for the future research. So, and they are giving that if we, this results what they obtain, so this gives better hope, better hope or better inspiration for the upcoming work.